and welcome to this, the first in the series of In Conversation With that the ASSAf EO has with exceptional scientists that we have in our midst. And this morning, it is my absolute privilege to invite Dr. Val Munsami, the CEO at the South African National Space Agency. Well, I'm not sure if you may remember, but there was a time that we were trying to source out new or alternate premises for the academy. And we actually had a plan where both SANSA and ASSAf was going to share a building.
It's still on the cards.
Yeah, but it kind of fizzled out. And in any event, 3 years have gone by almost. But in any way, it would have been excellent to have had the opportunity for that to have happened. Nonetheless, colleagues, I just want to say we are in for an out-of-body experience with some resonance on information on some of the work that SANSA is doing. And to share that with us, we have today Dr. Munsami, who is a physicist by training, but along the way managed to secure a master's in business leadership and a space studies diploma and certification in international airspace and telecommunications law. So as you can see, he's managed to augment his interests, supported by appropriate background in certification to be able to do this. I mean, his abridged CV reads like my long CV. But just to say that he has worked in some really remarkable places, including the Secretariat for the Non-Proliferation of Weapons of Mass Destruction. I mean, we did learn about mass destruction during the previous era of the US government, but I wasn't aware that we had a similar sort of program, and has been involved in multiple bilateral and multilateral engagements across the African continent. And I'm not going to read in detail all his accomplishments because I'm sure some of that is going to come out in his presentation. You have the details of his abridged resume in the flyer. But what is very apparent is that Val has managed to bring together multiple activities that he as CEO and his team have been able to do at SANSA. And I'm sure he's going to tell us about some of these under the theme of reimagining the national space sector. And so Val, without much more wastage of the time, I will now hand over to you to lead us into your world of what's happening at SANSA. Thank you, and over to you.
Thank you, Himla. Appreciate the kind. I'm going to share my screen very quickly and then kick off. And I'm going to switch off my camera just to save some bandwidth, if you don't mind. So I chose to speak around reimagining the space sector, and the narrative is quite a simple one. I wanted to start off by just demystifying the benefits of space science and technology. And the reason why I wanted to do that is because normally when we talk about space science and technology, immediately the mind is cast towards, landing on the moon or going to Mars. And actually there's a lot more to space science and technology that we don't realize. So I wanted to bring that into sharp focus. And then I wanted to give you a flavor in terms of our own national space capabilities and the core capabilities that we have on the ground. And then also give you a perspective as to why space capabilities are important for the country. And then what's happening inside of SANSA and actually the national space sector. And it's poised for significant growth at the moment, and I want to share that perspective. So let's start with demystifying the benefits of space science and technology. Now, we'll put it in this very simple terms. We seem to talk about orbits. Satellites are orbiting around the Earth. But let's try to understand how we get satellites into orbit. So let's assume you're standing on the ground. You take a tennis ball or whatever object, and I ask you to fling it. So you fling it at distance A. Then I say, okay, can you throw a little bit more energy into it? And so as you put more force behind it, it goes even further. So I said, okay, let's do it again and put a little bit more energy into it. So you do that again and again. But remember, the Earth is not flat, it is round. So what actually happens is that this is called the Newton guns experiment. So you keep throwing it further and further. And at some point in time, this object is falling towards the Earth. But because the Earth is curving away from the object, so the object is continuously falling towards the Earth, and it goes round and round the Earth. And that's what we call an orbit. So you have different orbits around the Earth, okay? And the orbit that's closest towards the Earth and that we normally use for putting satellites in what we call low Earth orbiting satellites, so your remote sensing capabilities are in that particular orbit. And I'll speak about what I actually mean by remote sensing just now. And then as you go further away from the Earth, you can get to a point around about, let's say, 36,000 kilometers away, where the rotation of the satellite is exactly 24 hours. So as the Earth is rotating on its axis, this particular object is also rotating at exactly the same speed. And the important thing to note is that satellite is exactly the same point above the Earth at all times. That's called the geostationary orbit, and I'll show you how we use that in terms of servicing some of the the applications we use on the ground. So this is effectively just to introduce to you the notion of putting a satellite into orbit, and that's how we use a launch vehicle to actually throw an object into space, and it's continuously falling towards the Earth. So in effect, you have all of these satellites that are just beaming and orbiting around us. And I've just put a few satellites, but actually in terms of operational satellites, there's about 2,000 at the moment. And there's about 5,000 that are defunct. That means that are not operational. But we have a serious problem. There's orbital debris. You might notice that now and again, some clever country decides to go and smash a satellite that's used up, and that's to demonstrate, their power and their might, that we can put a ballistic missile into space and target at pinpoint accuracy any object. And that's just, the big boys trying to outplay each other. And the problem with that is once you smash a satellite, you smash it into thousands of bits, and those thousands of little pieces are actually going into space and orbiting in space. And there's a huge risk that these fragments can hit your satellite. And so collision avoidance is becoming a huge issue. More importantly, there's now mega constellations coming online. So for example, Starlink, which is owned by Elon Musk, they're talking about 2,000 plus satellites. OneWeb is 900 satellites. So there's a whole proliferation of satellites coming through, and I'll talk about the utility of these satellites. But I just wanted to give you the concept of how we put satellites into orbits, essentially. So let's look at it from an Earth observation point of view. Now, it's very simple, explanation, and I'll try to explain what's actually happening in this diagram. Effectively, what you're doing is you're putting a satellite on the extreme right with optical imaging capability. So this is essentially a camera system on board a satellite that's taking photographic measurements on the ground. And effectively, the sun is streaming its the sunlight across the horizon. You get sunlight reflected of different objects. So what I've given you here as an example is a sunlight reflecting off a tree structure. But if you look at it at the leaf level, at each individual leaf, what's actually happening is that sunlight has multiple wavelengths. So you talk about the rainbow spectrum. If you split it through a prism, as an example, you see multiple colors coming through. So if I look at the primary colors, red, blue, and green, what's actually happening at the micro level, the leaf is actually absorbing the red and the blue, but is allowing the green to come through, to be reflected. So when you view the tree structure, the leaf structure, you actually observe it as green because it's only the green component that's reflected off. Okay. This reflected light actually is reflected back into the satellite or onto the satellite imager, and we take a photo and we download that and we can figure out what's happening on the ground. But it's a little bit more intricate than that, because all I'm showing you what you can see in the visible part of the spectrum. So don't get frightened about the next graph. I'll try to explain it to you. When we look at lights and radio waves, and, you know, you go into a doctor's, let's say, to take an X-ray, they're actually passing electromagnetic radiation through. And when you're looking at X-rays, they are very short wavelength electromagnetic waves, which means they're very high energy. So they're able to pass right through your skin structure, but not through the bone, so you can image the bone. So that's at the high end, short wave, very high energy. When you go to the very long wave, that's your radio wave. So when you listen to a radio station, it means that your wavelengths are very long, but low energy, okay? And what you see in this graph is essentially a spectrum of sunlight being reflected off a plant structure, okay? In your extreme left-hand corner, the 500 nanometers, okay? That little blip is all you and I can see. That's called the visible spectrum, around about the 500 on the X scale, okay? Everything to the right of that blip, we cannot see. So that's going into what we call the near infrared, short infrared. And so that's in the thermal band, essentially. But what I wanted to demonstrate to you is that in terms of the previous slide that I showed you, the sunlight hitting a plant structure, you're looking at it, but you're looking at it in different parts of the spectrum, not only the visible, but in the near infrared and short infrared, and so on. And the interesting thing is that when you get into the near infrared and short infrared, you can now distinguish, because each different plants have a different spectral characteristic. So if you use this and you can calibrate it, you can figure out that you're looking at a maize plant, you're looking at just pure grass or wheat. So you can characterize what kind of crop structure you're actually looking at from space, okay? Just by looking at the cell structure. Another important element about the cell structure is so we put satellites into what is called sun synchronous orbit, which means that when a satellite comes over, let's say at 9 o'clock in the morning, it will come through at every single day at 9 o'clock in the morning. So when you take an image at 9 o'clock in the morning, you can compare from one day to the other. So you could look at any variations in some of these spectral characteristics. So for example, you can see if a cell structure is changing, which means that you know there's some disease encroaching in the crop, or maybe there's some locust that's invading the cells, the plant itself. So if there's any changes in the cell structure, you can figure out whether there's as I said, there's a disease or whatever. And you can look at whether you need to fertilize the crop or not. When you go to the further right, you're starting to impede on what you call the absorption bands. Now you can pick up how much of water content is actually in the plant from space, okay? And actually we use this kind of application to also regulate how much of water farmers are actually using. So, you know, a farmer, in terms of the regulations, have to declare how many kiloliters of water they're using in the farm. And we can calibrate this from space to say, actually, what you've recorded and what we're observing is too different. And we can take this matter from a regulatory perspective. So you can see the richness of information that comes from satellite sensors. And we use this kind of information for precision farming. So you can tell a farmer when to fertilize and when to water the plants, okay? So there's rich information that has utility in terms of everyday life, agriculture being one example. By the way, you can actually use this example as well. So for example, if you're imaging a water body, let's say a huge lake, and suddenly one day you figure out the spectral characteristics has changed. And if you go and investigate, you might find there's cholera creeping in the water. And that you can actually see way before you see it in the visible part of the spectrum. Okay. So very powerful tool that you can use from space. And here's an example. You know, the red areas are essentially showing agricultural area that's stressed. And if you go actually in the field and you do validation studies, if you go in the field, you can see exactly that very same spot we're showing in the map. The maize crops are all dried up. There's drought. Okay. and there's not enough irrigation in those fields. So you can actually validate on the ground what you're observing in space. I wanted to show another application, space science. We don't seem to realize that we're continuously being bombarded by particles coming out of the sun on a daily basis, and that affects technology on the ground. So the sun is essentially, let's say, it's a nuclear furnace, and it's a, there's a lot of thermal nuclear reactions that are happening, and you're changing hydrogen, and you're converting that to helium, and you're producing all sorts of particles. Actually, you're producing gamma ray particles as well, coming out of the sun. But on a quiet day, when nothing seems to happen on the surface, there's continuous plasma that's being spewed out of the sun. On a very quiet day, speed, the ambient speed of that plasma is around about 400 kilometers per second. So it's quiet, but it's very energetic. If you have to travel from Pretoria or Johannesburg to Cape Town, you will do that in 3 seconds, essentially. That's how fast this plasma moves. But the sun goes through different cycles. We talk about an 11-year cycle, sunspot cycle. So it gets very active, and then it starts to get inactive. When it gets very active, you have a number of sunspots or eruptions on the surface of the sun, and you see a few of these things. And one of them is coronal mass ejection. So in certain parts or on the surface of the sun, you get this violent ejection of plasma. And those plasma can travel, bursts, can travel up to 800 to 1,000 kilometers per second. Okay, and that's very, very energetic. The only thing, and by the way, if we did not have a magnetic field, if Earth did not have a magnetic field, we'll all be fried. In fact, we won't even exist on Earth. So the only thing that's protecting us from that direct radiation is the Earth's magnetic field. Simple physics will tell you, and this is Maxwell's equation, if any of you are physicists, that that radiation cannot move across the magnetic field line. It actually gets trapped in the magnetic field lines. Okay, so the Earth's magnetic field is actually protecting us from that radiation. But what actually happens is the Earth magnetic field, as it traps the magnetic field line, on the night side, you see a little tail structure. It starts to load the tail structure so that, it's like pulling a slingshot. If you keep pulling the sling and suddenly it cannot take it anymore, it snaps. That's essentially what happens in the Earth's magnetosphere. The tail snaps. And when it snaps, all of the energy in that magnetic field lines really gets catapulted towards the Earth. And the only place it can go is in the polar regions. And this is where the auroras come in, by the way. These particles, charged particles, the ions and the electrons, they get dumped into the polar caps. And what actually happens when you look up into the night sky, when you get excitation, so you've got oxygen and nitrogen sitting in the ionosphere. But the simple physics says that if you hit an oxygen atom with an energetic particle, it rises up into different energy levels, but when it wants to come back down, it wants to force itself back to the ground state. It gives off light and it gives off energy. So oxygen gives off the greenish hue that you see in the auroras, and nitrogen gives off the pinkish hue that you see in the auroras. So in the North Pole and the South Pole, you see these night sky lights up into a greenish pinkish hue, which we call the auroras. And that's effectively because of what's coming from the sun. And by the way, there's a lot of technology. Satellites get destroyed because of these charged particles. And actually last week, Elon Musk launched at one go 49 satellites into orbit. 40 of the 49 satellites were destroyed because of activity from the sun, a solar storm. Okay. There's also effects on the ground because you have big current systems in space. They actually, I think it's even in high school physics, when you talk about Lenz's law, if you have one piece of wire where you induce a current, and if you put another piece of wire close to it, you actually find another current induced in the second wire. And that's essentially what happens. If you have a current system out in space, it induces current on the ground. And some of these currents flow into our electrical grid lines. And we've seen instances where even ESCOM transformers are actually destroyed because the current system is so intense, it saturates the transformers. This effect is actually very, very prominent in the higher latitudes towards the North Pole and the South Pole. But it can be very disruptive. And I'll come back to another application that we're currently working on. But I just wanted to give you a general feel of the physics behind solar storms. So what we do at SANSA is we measure the effects of what's happening out in space from the ground. So we have ground sensors, magnetometers, we have ionosondes. So magnetometers look at how the magnetic fields are changing over time. And we have magnetometers strewn all over the Southern African region. And by the way, when you're flying an aircraft, the modern day is to use global navigation satellite services. So you're using satellites to navigate. But from a defense point of view, those satellites can be switched off over your region. And the only fallback that you have is a magnetic compass. Okay, most of you will remember the magnetic compass. Now think about it this way. If you're flying from Johannesburg to Cape Town and your magnetic field deflects not even a degree, let's say a fraction of a degree, and if you're using the magnetic compass and if you didn't know that that magnetic compass is deflected a fraction of a degree, you will not reach Cape Town if you're flying from Johannesburg. You'll be off course. So we need to figure out if there's any changes in the magnetic field lines in real time and inform the pilot that these magnetic field lines are changing. Okay, so this is very, very crucial for navigation and especially for the defense sector. Okay, so this is just showing you all the different kinds of instrumentation that we actually use to measure space from the ground. And I'll talk about that just now. And by the way, in the top left-hand corner, you see semblances of aurora that I mentioned just now. Just to give you a sense of satellite telecommunications, just to go through some of the applications. When you're watching, let's say, DSTV, let's say you're watching live sports over the weekend. I know I'm a soccer fan or watch Formula One as an example. Wherever the event is happening, there's live telecasting, and that signal is broadcast to a telecommunications satellite that is sitting at 36,000 kilometers above the Earth. That satellite is rebroadcasting it back to Earth. So at your home, if you've got DSTV, you've got a DSTV dish essentially. If you notice that all of those dishes are all pointing in the same direction, they don't point in random directions. And the reason for that is that they are pointing to the same satellite. They're getting the signal from that satellite. I'm not sure if you've realized in the last few days, the signal is actually interrupted because there's solar storms happening at the moment that's actually disrupting some of the signals coming through. So you get a break in transmission as well because of that. But what I wanted to demonstrate here is the utility of telecoms satellite. And satellites are used for that perspective. Navigation and positioning. And a lot of you would have GPS on your phone to go from, let's say, location A to location B. But effectively, what's actually happening is there's a receivers on your phone that are picking up signals from these GNSS satellites. So GNSS stands for Global Navigation Satellite Services. Okay, so GPS is a classical example. Effectively, the satellites have got very accurate atomic clocks on board. So when they transmit a signal, they're continuously transmitting signals from the spacecraft. And what is actually happening is your phone is intersecting these signals from multiple satellites. And if you can pick up the signals from, let's say, 3 or more satellites, you can triangulate on the surface by trigonometry or simple mathematics exactly where you are on the surface of the Earth. Okay, so you pick up the signal from the satellite, it tells you how long or how the duration from after leaving the satellite to reaching your receiver on the phone. And you get that from 3 different satellites. So as an example here, one satellite is transmitting, the delay from the satellite to the receiver is 5 seconds, another is 4 seconds, another 3 seconds. You can use mathematics to actually decipher what the location is on the surface of the Earth, okay? If you have a reference frame. So this is how GPS is actually working. It's intersecting signals from multiple satellites. And you need 3 or more satellites to do that. Okay, I try to give you a flavor in terms of the different applications and how it's important for life here on Earth. I've spoken about Earth observation. I gave you an example of agricultural use, space science, how it affects technology, and how we, especially now we're talking about the fourth industrial revolution, and we're becoming strongly reliant on technology. It's affected by space weather. Okay? I've given you a sense of how telecommunications work and how GPS, or global navigation satellite services, actually work. And by the way, I'm not touching on the broad spectrum of applications. I mean, there's a whole plethora of applications. So for example, if you go to your ATM in the bank, in the mall, that signal or transaction is going via a telecommunications satellite. The timestamp on that transaction is coming from a GNSS satellite because it's got atomic clocks and it's got accurate time, and you need accurate timing for every transaction because time is money. You know, if you delay, let's say for an hour before you can see the money in your bank, interest is being earned, and so that affects the whole economy. And the more you delay, the bigger the impact from an economic perspective. So you want very accurate timing. So all of that is enabled through space. And by the way, if you switch off all the space or the satellites at the moment, your economy will be crippled. So let's look at some of our national space capabilities. I think I've got about just over 15 minutes. So as I said, we measure space from the ground. We've got a research base in Antarctica. And by the way, 80% of the research that's conducted in Antarctica is space physics related, purely because all of the magnetic field lines converge in the polar caps. And so you'll see, for example, the center bottom is called a radar facility. It's tracking what's happening out in space. Okay. We also have Gough and Marion Island. We've got research bases there as well. And we also do field measurements from Marion Island and Gough as well, okay, and in Antarctica. And by the way, the only African country that has a presence in Antarctica that conducts scientific research there. How is this important? So let's look at the bottom, middle bottom. Here you have a submarine, okay? So we have got a considerable wealth of expertise in magnetic field measurements and how to demagnetize huge structures. So the guy on the top right is showing you the principle. So what they actually do is wrap a coil around a metal structure and they try to demagnetize, because a lot of magnetic structures have magnetic fields. The problem with that, since World War II, there's a number of countries that have put magnetic bombs on the seabed. Effectively, what these bombs do, they sense certain magnetic signature. They know what the magnetic signature of the enemies look like. And the moment those bombs sense those magnetic field lines, let's say a submarine or a frigate or a ship that goes over, it explodes and it destroys your submarine, it destroys your Navy vessel, as an example. So what we have to do is to demagnetize the entire submarine. And we go and wrap a coil, which is about 20 centimeters thick, right around the submarine, and we have a procedure to demagnetize a submarine or a Navy vessel, a frigate, as an example. And that takes about 6 weeks, by the way, to demagnetize, to make our Navy vessels safe. And all of that is provided by SANSA. On your right, as I said, your fallback instrument when you're navigating is your magnetic compasses. So you've got to you calibrate your magnetic compasses to be able to use them on board, especially in the Defense Force. So we calibrate all of the Defense Forces compasses, and we do that across the African continent. One of the other things I should mention is there's a new set of regulations that's been introduced in November last year. Sorry. If you're flying on an aircraft, let's say you're flying from here to Paris, all flights must now have space weather information on board. It's now internationally regulated because we figured out there's an aviation risk if you fly from space weather, okay? And I'll explain to you how that risk actually emanates. The interesting thing is for the African continent, whether you're flying from Europe into Africa or you're flying out of Africa, that space weather information will come from SANSA, the National Space Agency. Okay? And I'll show you in terms of the new facilities that we're developing, what we're actually putting on the ground. And the reason why you need space weather information on board, when a pilot is flying, on the cockpit, they are continuously communicating with the ground. So there's different ground segments. As they pass different countries, they continuously communicating with the ground segment to say, I'm here over your airspace, and then you get your local weather and what have you beamed up. Okay. Now, the way the pilot is communicating, the aircraft is emitting a radio signal. The radio signal is transmitted into space. It gets bounced off the ionosphere. The ionosphere is essentially a layer of charged particles. It gets bounced off the ionosphere, hits the ionosphere, and is redirected towards the ground. And it reaches the ground segment. And through this means you can then communicate with the ground station. Now, when you have a solar storm, what actually happens is you actually injecting a lot more charged particles in the ionosphere, whether it's electrons or ions. And what actually happening is these charged particles actually absorbing the signal. They're not retransmitting the signal. And what actually happens is the pilot cannot communicate with the ground signal. They lose communications essentially. You get a communications blackout. So the pilot is unable to communicate. The second thing is that modern aircrafts actually use the global navigation satellite services to navigate in terms of where they're going. Now, when these storms happen, as I said, the charged particles in the ionosphere gets heavily populated, and the signal from space cannot come through the ionosphere. It actually gets absorbed. And the second effect is that the pilot cannot see where they're going because there's no navigation signal coming from space into the cockpit. So they're flying blind essentially, and they have to fall back on magnetic compasses. And that's not the ideal. So you don't have HF communications, you don't have navigation signals, and that's an aviation safety. The third impact is that as you're flying, because you've got excessive radiation in the ionosphere, if you're flying long duration, your body is constantly being bombarded with radiation. And like you go to a doctor's office, surgery or, to do an x-ray, those gamma rays are hitting your cells, and they're actually killing your cells, by the way, as they impact or hit your cell structures. The same thing happens when you fly. These radiation particles go right through the plane, hit you on the skin, and they start to kill off certain your cells. And that can lead to cancer as well. And the worst part to be flying, by the way, is between South Africa and South America, or Southern Africa and South America. There's a region called the South Atlantic Anomaly, where is a weakened part in the magnetic field, where the radiation comes right down towards the ground. And if you're flying in that region during a magnetic storm, you're going to get overdosed with radiation. So these are the kind of reasons why you don't want to actually fly. And there are instances where flights are actually grounded. And the reason why I'm putting that on the table demonstrate how important space weather, understanding space weather, is even if you're flying long-haul flights. So just very quickly to give you a sense of the kind of infrastructure base that we have. On the top right is your assembly, integration, and testing facility. That still belongs to Denel at the moment, but we are looking at moving that facility into SANSA, and we have some funding, about 75 million rand, to completely upgrade this facility for our new satellite build program. On the top left is your Overberg test range. So this is a launch site where South Africa launched vehicles quite early, late in the 80s. And we had some of these launch vehicles going into space as well, or suborbital space. The big satellite in the bottom left is your heritage called GreenSat, that was built in the 80s, but was never actually put into space. So we've got some heritage that we're actually leveraging on as our starting base. Where South Africa is playing at the moment, there's two pathways that we're looking at. The one is nanosats, which is your CubeSats. So the one on your left-hand side is essentially the size of a loaf of bread, essentially. So this particular satellite was flown in 2018, December 2018. And what it has on board is it's got a payload that's picking up signals from your ship. So each ship should have a location transponder. And what the satellite is doing is picking up the location transponder from each and every ship that's on our coastline. Remember, our coastline is 3,200 kilometers. There's no way you can patrol that coastline from the ground. You have to do it from space. And we can pick up the ship's signals, overlay that with radar signals, meaning that a radar is a specific, what we call active sensor. So it's a signal that's emitted from the satellite, and you look at the reflected signal. So you can pick up a ship on the ocean's, on the ocean surface. What happens if you see a ship, but you don't see a location or beacon switched on? Now you can figure out there's some rogue ships on your coastline. And this is how we trap illegal fishing. And we've actually caught one ship out that came from South America to Port Elizabeth with its beacon off, but it actually had drugs on board. And the one on the right is your small sats that goes up to about 400, 500 kilograms. So those are slightly bigger satellites, and we use optical payloads. And the resolutions, you can get much higher resolutions on that satellite, right down to within a meter. So you can pinpoint an object in our car on the road, as an example, from that kind of satellite. It's getting down to about 30 centimeters, so which means that you can see much finer details from space as well on the optical side. A big asset that we have in SANSA is our ground station. We have over actually 70 antennas on the ground, and we use this to track satellites on a daily basis. So on our site for our national leads, we track about 18 satellite parcels on a daily basis. And there's a lot of services that we render for international clients. As I said, we're looking towards 70 antennas. In fact, we're just commissioning 20. 20 of those antennas are talking to 900 satellites at a time. These 900 satellites are now going to start providing global internet access. So you don't need to rely on fiber network anymore. You can rely on a satellite dish. You put a little dish the size of your teacup on your roof, and you can pick up a signal that will give you internet access. And you can get it in the rural area. You don't need any cabling. And all of this is coming online through space. And we call those teleport services. And that service is being provided by SANSA on the ground. Another important, got about 6 minutes left. We do launch support. So every time there's a launch from the US on Vandenberg or Cape Canaveral, or even the Europeans have launched from French Guiana, just on the northern end of South America. If you follow the red lines, they come over our footprint. So let's assume the US is launching a rocket that's going to the International Space Station. They completely lose sight of that launch vehicle. And the command and control of those launch vehicles happen over SANSA's footprint. And a lot of the commands are issued over our ground segment. And we're also ejecting the satellites in our footprint. And we switch them on, we do in-orbit testing. And so a lot of the launch support, in-orbit testing, all of that is done. And that's paid for services from which SANSA offers to the global community. On the Earth observation side, we're putting in what is called a data cube platform. So we have data, by the way, that satellite imagery that goes back to 1972, when the first Landsats came on board. Now, this is very important because we have actually archived and stored all of the data in our archiving system in SANSA. Now, let's say government wants to make policy decisions, let's say on a water body, but it needs historical data. So we look at evidence-based policy making. So it looks at the satellite imagery, analyzes it, and say, okay, the water quality has changed in this manner because of certain environmental conditions. And what the data cube is doing is it's stacking information, and you can now stack information according to a geolocation. So I can say in certain location in Hartbeespoort, I want to see how the landscape has changed from 1972 up until today. You get into the system and you can do that within a few hours. If you didn't have this kind of platform, a data cube platform, that can take you about 3 to 6 months to do it. Now we can do that within a few hours because of the information technology that we have on hand. And we're also looking at putting up a data visualization wall, where we can demonstrate a lot of these products and services. And this is just a sample of all of the government users that actually use our facilities. SBAS, satellite-based augmentation system. I gave you example of global navigation satellite services. The problem with the global navigation satellite services, you're picking up 3 or more satellites signals on, let's say, your phone. But the error signal on your GPS, if you go right to the bottom left-hand corner, can be out by at least anywhere between 5 and 8 meters. Sometimes you'll notice you're driving on a road, but it actually shows the car is driving on the side of the road as opposed to on the road. And that's because there's an error signal that's on the system. So what we have done is we put ground infrastructure in place to correct it. So that little blob on the green blob is essentially correcting that GPS signal. Now this, by the way, is very important for the safety of life. And actually the post office is very keen on these kind of services, because if you think of an informal settlement, and now you're taking, let's say the census is happening, and you want to know a post office address on each dwelling, if your error signal is out by 5 to 8 meters, you can't differentiate one household from the other. So if you can reduce it to within a meter, now you can put a post office box address, a GPS signal for each location, and add vector information onto that. How many people there, what's the income in there. So now you can look at it from a social sciences point of view as well. And by the way, even your social distancing during COVID-19, you cannot do that without the satellite-based augmentation system to figure out proximities. And so I'm just going to jump that. Why is the space important? When we started off the space program, we brought government departments together. Remember, government is responsible for making policy decisions, and they use satellite imagery for evidence-based policy making. And a number of government departments have what we call a geographic information systems unit inside of the government department that takes satellite imagery, look at the information, and use that to make the policy decisions. And now what we are doing from a SANSA perspective is assisting them. So we asked them the question, this is around about 2007, what is it that you want SANSA to assist when we establish SANSA? And we came up with a whole list of priorities. I'm not going to go through that. It's actually in our national space strategy, environment and resource management being one of them, health, safety and security, defense, peacekeeping and treaty, asset monitoring, how does assets move across our borders? All of that can be tracked from space. Innovation and economic growth, tourism, recreation. A big part, by the way, is technology spin-offs. And by the way, NASA and the European Space Agency, they publish thick volumes every year of intellectual property that is used in other sectors. By the way, I should mention baby nappies, baby food, cordless drills. You know, when you're taking a temperature, your temperatures, now that COVID is happening, all of that comes from space technology, okay? Water purification, all of that is happening from coming out of the space technology. So I'm just going to stop my clock. This is just demonstrating, by the way, that the importance of, so I'm just going to close this. My clock is, I'm done, but I'll just take a few minutes quickly, if you don't mind. This is just demonstrating how important these different priority areas is to different government instruments, the NDP, Triple Challenge, MTSF, and so on. So for example, if I take environmental and geospatial monitoring, it actually covers 7 of the 13 different aspects that's being looked at from the National Development Plan. Okay, and the same also applies across the different policy instruments. The SDGs, 60 to 70% of the SDGs actually require satellite information. Climate change is an example, 70% of the essential climate variables come from space. Okay. And just very quickly, where we are taking the space program, because of the limited funding that's coming from government, 2 years ago, we were only getting 150 million rands. We started to actively look for additional funding. We're now sitting around 350 million rand with the whole pipeline of projects coming through. But if we fast forward to the next 2 years, we're looking at about an 18 billion rand pipeline. And this is very quickly what it looks like: a telecom satellite, data cube, teleports, global internet traffic access, a concurrent design facility. I'll speak about some of these things just now, but this is a whole pipeline of projects that are coming through that collectively amount to 18 billion. And sorry, the DSI is also pushing the launch capabilities, which is about 4 billion rands as well. The big project that we're currently working on, then in fact, we're just concluding in the bankable feasibility study for about 4.5 billion rands, is to now start building a whole series of satellites that will be orbiting Earth, that will be collecting information in different spectral bands. We'll be upgrading our ground infrastructure, looking at upgrading our data infrastructure, working with industry to build products and services that's actually going to be used by government departments and the private sector as well. And so this is quite a big initiative that SANSA is embarking on. And then we spent about 100 million rand on the new space weather center. Remember, for the aviation sector, that information has to come from SANSA. So the bottom picture you see is an artist's rendition of the new space weather center. The top one is just demonstrating where we are in the current construction. So this facility will be ready in September and fully operational in September, and be providing space weather information to the entire African continent. We're also building a concurrent design facility. So if you have to design a satellite, it could take you about 12, 15 months to actually design a satellite. What this facility actually does, and we've partnered with the European Space Agency and building an exact facility, a replica of what you see here, maybe at a smaller scale, is if you ever bring in engineers sitting in this room and you start to design a satellite on the fly, you can now design that same satellite within 3 to 4 weeks, as opposed to 12 months to 16 months. So the cost comes right down, okay? And you can design satellites much quicker. And this is going to be part of the SANSA facilities that's on offer to the industry as well. We're also in conversation with NASA, JPL. So NASA has 3 deep space networks, one in Australia, Spain, and the US. So these deep space networks, they actually, if you have a mission that's going to the moon or to Mars, you have to communicate with the spacecraft. So these kind of antenna structures are around 30-meter dishes. So we're looking at hosting the 4th deep space network here in South Africa in a place called Maikesfontein. We've done the environmental impact assessment, and we're currently looking at getting the ground infrastructure ready. But this is about a 3 billion rand project that we are currently looking at. And so NASA, SANSA will be supporting space exploration missions as well. By the way, we're already doing that. We supported the Solar Parker mission that's going to the sun. We supported the Chandrayaan mission from the Indians that were trying to land a rover on the moon. So we do a lot of space exploration missions, including landing on Mars as well. That's done from, supported here from SANSA. I'm not going to touch on this, but because of the change in the scope of what we're trying to do, there's a lot of changes that's happening inside of SANSA. We've just changed our business model, our macro structure. So we're not restructuring, we're actually growing the organization because of all of the opportunities coming through. We're changing the organizational culture, which we started 6 months ago. We're overhauling of our policies and systems. So all of our SANSA policies, over 70 of them, we're completely revising them and aligning them to a new business model. We're doing a complete rebrand in terms of creating brand visibility so we can effectively communicate the work that we're doing going forward. And I thought this was an important element because the organization itself has to be reimagined in a way to be able to cater for the growth expansion. So Himla, I think I've taken a few minutes extra, but thought I'd be useful just to get to the final slide. Thanks for your attention.
Thanks, Val. Wow, I mean, this is remarkable, and this is the kind of thing that we hope to achieve during these sorts of conversations, getting to know the kind of work that goes on in the country and how it intersects with our daily lives. I mean, you've given us examples that are, you know, incredible wow factors, from the structure of a leaf and how that is coordinated with the sorts of technologies that satellite imaging and management brings is just remarkable. So before I take a few shots at engaging a discussion, there have been a few comments that have been coming through in the chat box, which Renata has sent to us. And they have 2 from Mark van Heerden. And the one question he asks is, if the atmosphere above South Africa should experience a hit from the solar superstorm that would generate a geomagnetic storm, is there a possibility that the electrical grid can be overwhelmed and damaged? So that's the first one.
Okay.
Do you want me to add the others so you can take them together, or you want to address that one?
No, I can add others as well.
Okay, so that's the first one. And then the second one is, does South Africa have a protocol in place to minimize damage to the electrical grid should a geomagnetic storm hit us? And if so, is your agency involved in an early warning system for such an eventuality? And do you know if Eskom can implement an emergency shutdown of the electrical grid should a geomagnetic storm hit us? How can we as citizens be better prepared for such eventuality, such as massive geometric storms, if they should hit South Africa?
Okay.
All right, I'll let you get through that before I take more. So colleagues, if you want to ask more questions, just put it on the Q&A or chat, and Renata will direct them to me to ask to Val. Thanks.
Great, thanks. So let me take the question. So if there was a superstorm, as I said, you will have induced currents on the ground, okay? And if the storm is intense enough, yes, it gets into the electrical lines and it can saturate. And we have seen damage happening on the electrical grid in terms of transformers being damaged. So if it is a superstorm, the answer is yes, it can. We were quite puzzled by this because we thought this was a high latitude phenomenon and not near the equator, but it seems like it does. If it's intense enough, it can get lower down in the latitude. In terms of protocol, we've done some work with the Eskom in trying to assess the level of damage and how do we mitigate against some of this damage. I can tell you there's no protocol in place at the moment, but we can, at least with a day or two's advance notice, figure out when a storm is approaching. So remember, the storm is approaching from the sun, and there's certain satellites called the libration points. So we have what is called L1 libration point. So if I can explain to you, simple physics will tell you that if you put an object between, let's say above the Earth, Newton's laws, it's attracting that object towards the surface of the Earth. Now, if you put the sun on the other side, the sun is also attracting it. So at some point in time, the force of attraction towards the Earth and the sun is balanced out. So that's called a libration point. So you can put a satellite there and it will just orbit. So these satellites actually is continuously collecting information and it's transmitting it back to Earth. What is the magnetic field structure look like? How much of plasma is coming through? So it's giving us advanced warning. So we can, depending on how fast the storm is moving, with probably a day or even less than a day, we can figure out that there's a storm approaching. The way to circumvent damage, by the way, if you're operating a satellite, is to switch your satellite off. That's the only thing you can do at the moment. Because if you keep your satellite on, effectively the electrons and the ions, they get into the satellite and they damage the electronics. So switch off your satellite. And the same thing would apply to the Eskom grid. Unfortunately, it's not load shedding, but you just switch it off until the storm is passed. Okay. At the moment, we don't have those protocols in place, but we've done some work. And as I said, the effect is actually more enhanced on the high latitude. So it's not electrical grids only, by the way. It's also, if I can explain it very simply, your oil pipelines, especially in the Northern Hemisphere, if you think about how rust happens, it's actually little electrical currents that is causing oxidization. Mm-hmm. And the moment you get current structures flowing in an oil pipeline, you are accelerating the rusting process as well. And these things are actually influenced by what's happening in space as well. And you get erosion of oil pipelines, and that is quite expensive as well. Yeah.
Related to that, those questions, somebody asks whether it is possible to harness energy from space for use on Earth.
That's a very, very interesting question. The answer is conceptually, it should be possible, but technologically, it's very complicated. So for example, satellites use energy from the sun. They have these solar panels that's actually collecting energy from the sun. The same with the International Space Station. You'll see there's big solar panels deployed. So effectively, and by the way, there's a lot you can learn from the International Space Station, because if you think about it, it's a closed system, right?
Right.
You're going to recycle your waste. There's nothing that goes to waste. All of that technology comes back down on Earth. So effectively, from an energy point of view, we are using the energy from the sun to power some of these systems. And now there is some talk and a lot of R&D that's being done is how do we collect that energy and beam it back down to Earth. And there's new technologies that we're looking at, lasers and microwaves from space emitting that energy back down to Earth. But it's still early days, but it is possible in terms of what's.
Well, what you've demonstrated is the incredible high skill and utility of skills in managing and utilizing these various resources that you have in the diverse ways in which you've shared with us.
Yeah.
How well is the South African community prepared for these sorts of ventures? I mean, in other words, we always talk about skills and capacity development. Are we on a trajectory to have this shift of skills development to take on these new expertise that's required to move with the changing global environment?
Yeah, so Himla, at the moment, we support about 60 master's and PhD students on an annual basis. And this is in the space sciences domain. We also have on-site accommodation for about 20 students inside of SANSA in a place called Hermanus. And they're actually directly supervised by our staff. So we have got about 15 researchers on the ground, which are internationally recognized, by the way. Our research publication per annum per researcher is above 2, which is above the national average. In fact, about 3 or 4 are hitting about 4 per annum. So very productive researchers on the ground.
Right.
And then we're the only, by the way, public entity that has a research chair assigned to it. Normally they're assigned to universities. SANSA is the only one that has a space weather research chair. So we're doing a lot in terms of building capacity, including space engineering, remote sensing. And by the way, some of these skill sets don't actually stay fully in the space sector. They go into the banking arena.
Yeah.
If you're looking at data analytics, that's where it's needed as well. So it's not only for space, it's for the broader economy as well. So the answer is yes, we're doing a lot, but we're also working on a skills development strategy, which the ministers asked us to look at and expand our skills base. Because what we do from an engineering perspective, remember, in space, you don't have a second shot. If you put a satellite up there, you cannot afford for it to fail. You cannot go and fix it. So your engineering quality requirements are much more stringent than any other domain. So if you can adopt these quality standards, you actually benefit a lot more of the economic sectors as well. The concurrent design facility is one example. So upskilling in the space sector, you can actually plow that into other sectors as well.
Right. So space science is not only like what Elon Musk is doing, because we have a kind of concorded view based on what is out in the public domain. So thanks to I think maybe one of your colleagues who has answered, Deline, who has answered some of the questions in the chat box. There is another question also about magnetic storms. Is it possible that the geomagnetic storms can induce increased currents on the electric grid?
Actually, it's not a question. Amal was actually saying it is possible.
Oh, is it possible? Okay, so there's also a response. Okay, I didn't pick that one up. Well, the question I had is, at some point when we chatted informally, you mentioned some of the work SANSA had done during the COVID pandemic, particularly during that very stringent lockdown phase, where you were kind of managing, what was going on in the parking lots at supermarkets, etc. Could you please share with our audience some of the work that that you guys have been doing during those lockdown periods?
Yeah, so when you're looking at the let's say, COVID vector as it's spreading all across the country, so you can look at it from a geospatial perspective. So you know, if you have a satellite map, what your population density sort of looks like, okay? And if you provide that map, and we used to provide that to the CSR, and they used to overlay in terms of how the disease was developing over time. So that was very crucial baseline information in terms of population density and how this disease vector was spreading. What we had actually, there's several other applications that we brought online. So for example, when the president issued a lockdown, we started to map out, remember with your GPS, we can now figure out how vehicles are moving on the road as well. Remember, if you're using Google Maps as an example, Google Maps will tell you there's a traffic jam ahead because it's figuring out how the traffic is moving, and it's figuring out there's something, there's a problem down the road. So we can take that kind of information, turn it on its head. And what we found is that when the president issued a lockdown and he says, in 24 hours, we're going to close down all of the, the provincial borders, and you can see on the road, all of the traffic just moving between the provinces immediately. And then you can see, the open shopping malls. You can see on the car park how many cars are in the malls. And so now you can start to pick up in terms of how people are moving around during the COVID-19. By the way, the footprint in terms of your built structures, you can now figure out how many buildings there are, how many people are in each building. And that's very important if you want to deploy, let's say, health workers on the ground to do testing, or food parcels, or whatever the case may be. So those are kind of examples that we use. And by the way, the space weather, your defense force and your police force that were deployed on the ground, they actually use exactly the same technology, HF or radar communications or high frequency communication, where it's bounced off the ionosphere. And we can send them information in terms of what frequencies to tune into to be able to communicate with one another. So there's a lot of space technology being used in the middle of the pandemic as well.
Yeah, and I have to ask this, given the remarkable satellite abilities that we have, how is it that we still can't find the whereabouts of that Malaysian aircraft that disappeared off the grid in 2014? Yeah,
so first of all, the aircraft was lost because we had no global navigation satellite services. This probably was not transmitting at that point in time. And I think it went missing over airspace, over the ocean somewhere, and completely lost sight of it. So wherever it is, the signal
even all those damaging weaponry in the ocean bed that you protect ships with could not help us?
Well, it depends how deep the wreckage is actually beneath the surface. You can pick up surface, wreckage that's on the, let's say, lying on the surface of the ocean if you're using radar technology. But once it gets below a certain depth, you cannot pick it up, unfortunately. So there's only a skin depth that we can see below the surface.
Right, right. And then a question somebody has asked me to ask you is, what can space science tell us about life outside of, the commenting, is there life outside that we haven't checked yet?
I think this is an open-ended question, Himla. We just don't know yet. I mean, there's a whole community that's mobilized called SETI, the Search Against Extraterrestrial Intelligence. And we haven't found any signal as yet, but they're still looking. I always make the joke, yes, there is intelligent life out there. That's why they haven't bothered to contact us.
Well, I mean, I'm sure we could go on and on. You have, there is a hand up, Cedric. Renata, could you allow Cedric to come in?
Yes, sure, Himla. Just find him.
Colleagues, just bear with us for a few more minutes so we give others an opportunity to engage with Dr. Munsami.
Cedric, you can unmute yourself.
Cedric, you want to ask a question? Please go ahead. Sorry, Val, I'm not sure what's going on there.
Not a problem.
Lynette, did you have a question? I saw a hand, or it's disappeared. Somebody also asked a question, but I think you did answer it, about alternate options for connectivity rather than the internet. You did mention the options of some satellites that could be utilized for that.
Yes. So these are the teleports that we've been talking about. So there's one called OneWeb, which is about 900 satellites in low. There's another one by Elon Musk, Starlink, which is over 2,000 satellites. So as these satellites are orbiting, they are providing internet connectivity on the ground seamlessly. So that's coming, and it's going to probably be disrupting the market.
Why the significance of the 37,000 kilometers to place satellites? Is there a range at which they need to be positioned relative to the Earth? I know you started off with your first slide showing us, the angle and the movements and orientation of the Earth relative to satellites.
Yeah.
But why that range?
So it's a simple physics, Himla. So if you think of this as your Earth, if you're on a low orbit, let's say about 400 kilometers per second, the period, the revolution that the satellite goes around is about 90 minutes. So every 90 minutes, the satellite comes back. The Earth is rotating, right? As you start to go higher and higher, that periodicity increases.
Okay.
Okay. And one of the 36,000 kilometers is where 24 hours. Okay. The fact that it's 24 hours means that as the Earth is turning once every 24 hours, the satellite is staying above one location. And that's a geostationary orbit. So the further you go away from the surface of the Earth, the periodicity increases. The closer you get, the quicker it goes around, if I can put it.
Okay, thanks. No, and then the question that's intrigued me a lot is, like even in your introduction slide, where you show Earth as that globe, right? At what point, when you travel from Earth into outer space, do you see Earth in that way? I mean, like, what is a break point where you start to see Earth as that globe?
It's quite amazing, if you are just above the Earth's surface. And by the way, there's a whole debate in the United Nations as to at what point do you need to get to be in outer space.
Yeah.
Now, this debate is very, very important, by the way, because in South Africa, you have airspace. So this is our sovereign space. When you get to outer space, it's not sovereign. You cannot claim sovereignty for it. Okay? So there's been this debate as to whether you can have a satellite over South Africa above, so there's all sorts of definitions. 100 kilometers seems to be one of the accepted definitions, but it seems like the boundary is moving. But if you can get above 100 kilometers, then you can see the Earth as you would see it from space. You'll see it's sort of blackened. You don't experience it as you would from the ground in terms of the sunlight. But of course, the further you go away from the surface of the Earth, then you see the Earth sort of shrinking. And the first classical image that was taken as the Apollo missions as they were getting closer to the moon. And they looked back and they took that image and they realized this is amazing.
Yeah, and what was I gonna ask? Oh, it slipped my mind now. I had a question formulating in my brain, and it just disappeared as I processed your answer. But nevertheless, I mean, I guess you have demonstrated to us that the potential of satellites and the way in which it engages in a multi-sectorial way is absolutely beneficial in multiple sectors of society. And of course, in some instances, the real-time effect of that data needs to be processed by the users in real quick time.
Yeah.
And so I guess that is what my question was related to. To what extent do you have to kind of collate information, etc., with a turnaround time for its utility to the users, or is it something that you all have worked algorithms on, given managing and monitoring data over periods of time, to say that, like these weather patterns while a flight is in progress? I mean, that is a real-time information. So how is the gathering of information managed within the computers so that the users can evaluate it in real time?
So that's a very important question, Himla. So for example, Earth observation, remote sensing, like the agricultural applications that I've shared today. Previously, what we used to do is when we used to track a satellite, and we do what is called telemetry tracking and command, on the telemetry side, we used to extract the image from the satellite and then put it into an archive. And if a user wanted to engage with that satellite image over a certain area, they would then analyze the data, convert it and analyze it. What we are currently doing now with the data cube, and that's the trick with the data cube as well, we're doing these satellite passes, about 15 to 18 of them on a daily basis. As they get into the system, they are immediately sort of transformed. So we put them into what we call analysis-ready data. As the imagery is downloaded, they get converted and put into the system. So you can immediately have access to it. In fact, we start to now look at developing mosaics. So you take little satellite images and you stitch them together and you can form a satellite map over the country, okay? Each time there's a satellite image that comes through, you can convert that and put it into the mosaic and continuously update the mosaic over the country. And that's essentially where we're moving to at the moment. So now you can start to look at imagery within a few minutes of it actually being downloaded, as opposed to what we used to in the past, being a few hours and months after minutes. Technology is advancing.
Right. And the question that Cedric would have liked to ask was, since SANSA can get an early warning system for loss of HF communication for aircraft navigation, what is the solution for that? And I guess you know what HF communication is.
Yeah, it's high frequency.
High frequency, yeah.
Okay. Yes, so from a SANSA perspective, we've developed a number of tools, including for the Defense Force. So essentially what happens is this communication loss is in very selective frequency bands. So it happens within a certain frequency range. So we've developed artificial intelligence tools that can help us to decipher at what frequency you should ship. So if you normally communicating in a certain frequency, we can tell you now, actually move it into this frequency band, okay, which is less affected. So those are the kinds of tools that we are working on, and one that's actually internationally competitive at the moment. We just need to get our locals to use it.
Yeah. Anyway, colleagues and Val, in the interest of time, I need to bring this session to a close. But what a remarkable feast of the sciences you have given us today in issues that, we all have these little things in our hands. We use it for multiple purposes, and yet the science behind all of it is not fully understood by all of us. And I think you've given us a window into your world. And I know that given the shortness of the time that you gave us a a kind of glimpse into it. And we are so blessed to have had the opportunity to have you speak with us with some degree of sadness on your last month at SANSA. And we wish your team continued greatness as they go along. And as your colleagues know, SANSA and ASSAf have an MOU, and we look forward to an engaging future because we would want to be in contact and to see how we can learn from you and maybe be at the level of service of some of the multitude of things that you have on offer. So from all of us at ASSAf, and for those who stayed with us for the duration of the session, thank you very, very much for bringing to us in eloquent, simplistic, visual ways a way into your world. And we wish you well on your onward journey and hope that we could continue to stay in touch wherever your new aspirations take you. All the best, and thank you so much.
Thank you.
Cheers, and thanks, colleagues, for giving us some additional time. Bye for now.
Bye.
Bye.